Welcome everyone. Today we are diving into a fascinating mathematical topic called the transition probability matrix. Imagine you want to predict tomorrow's weather based only on what the weather is like today. How do we capture that mathematically? This matrix is the ultimate tool for taming randomness, and by the end of this lesson, you will understand exactly how it works. To begin our journey, let us think about how systems change over time. A system's current situation, like the weather being sunny or rainy, is called a state. When the weather changes from sunny to rainy, we call that a transition. Because these changes are random, we can only talk about the chances or probabilities of them happening. We organize all these chances into a neat, square grid. The rows tell us where we are right now, and the columns tell us where we might go next. Now that we understand what states and transitions are, let us look at how we write this mathematically. We use a capital letter P to represent the entire transition probability matrix. Inside this matrix, every individual chance is written as a small p with two subscripts, I and J. The first subscript I is your starting row, representing exactly where you are today. The second subscript, J, is your destination column, representing exactly where you will be tomorrow. If a probability increases, that specific transition becomes much more likely to happen. This matrix we just built has to follow strict rules to make logical sense in the real world. First, you cannot have a negative chance of something happening, so every probability must be 0 or greater. Second, and most importantly, if you add up all the probabilities across a single row, the total must equal exactly 1. Why? Because if you start in a specific state today, you absolutely must go somewhere tomorrow, even if you just stay in the same state. A matrix that follows this rule is called a stochastic matrix. So, we have established how to predict one step into the future. But what if we want to predict the weather for the day after tomorrow, or even a week from now? This brings us to higher transition probabilities. Amazingly, we do not need to invent a complicated new formula to figure this out. The matrix itself already contains all the information we need. We just have to use standard matrix multiplication to unlock it. Let us see the mathematical form of this idea. To find the probabilities of moving between states in exactly n steps, we calculate p superscript parenthesis n. To get this, we simply take our original one-step matrix P and multiply it by itself n times using standard matrix multiplication. So, for 2 steps, we calculate P squared. As the number of steps increases, the matrix perfectly tracks all the possible branching paths the system could take. Increasing the variable n simply looks further and further into the future. Before we move on, let us see this with a concrete example. Imagine a simple weather model. State 1 is sunny and state 2 is rainy. If today is sunny, there is an 80% chance tomorrow is sunny and a 20% chance it is rainy. If today is rainy, there is a 40% chance of sun tomorrow and a 60% chance of rain. We place the sunny starting chances in the first row and the rainy starting chances in the second row to build our matrix P. Continuing with our weather model, the question asks for the probability of it being rainy 2 days from now, assuming today is sunny. To find this 2-day probability, we must multiply the matrix P by itself to find P squared. We use standard matrix multiplication, multiplying the rows of the first matrix by the columns of the second. This arithmetic carefully accounts for all possible paths, like sunny to rainy or sunny to rainy. Let us look at the final result of that multiplication. We get a new matrix containing all the exact 2-day probabilities. Since we started on a sunny day, we look at the first row. Since we want to know the chance of a rainy day, we look at the second column. The value there is 0.28. This means there is exactly a 28% chance of rain 2 days after a sunny day. Now that we have calculated short-term steps, what happens if we look far into the future? If we keep multiplying the matrix by itself for a very large number of steps, something magical happens. The probabilities stop changing and settle down into a fixed, stable pattern called the equilibrium distribution. Just like shuffling a deck of cards until it is completely mixed, the system reaches a natural balance and completely forgets which state it originally started in. To find this natural balance mathematically, we use two crucial equations. The first equation says that if you take the stable row vector pi and multiply it by the transition matrix P, the result is just the exact same vector pi back again. Taking one more step does not change the overall probabilities. The second equation states that the sum of all these long-term probabilities must equal exactly 1, representing 100% certainty that the system is in one of the available states. Let us apply these steady-state equations to our weather model to find its natural balance. We want to know the overall percentage of sunny versus rainy days in the long run. We define a row vector pi containing pi1 for sunny and pi2 for rainy. We then set up our matrix equation, multiplying this unknown vector by our known transition matrix P and setting it equal to the unknown vector itself. Continuing with our calculation, we multiply the row vector by the first column of the matrix to create an algebraic equation for the sunny state. We get 0.8 pi1 plus 0.4 pi2 equals pi1. By subtracting 0.8 pi1 from both sides, we isolate the variables. Dividing by 0.2 reveals a clear ratio. Pi1 equals 2 times pi2. In plain English, there will be twice as many sunny days as rainy days. To find the exact numerical values, we bring in our second rule. The probabilities must sum to 1. We substitute our ratio into the sum equation, replacing pi1 with 2 times pi2. This gives us 3 pi2 equals 1, meaning pi2 is exactly 1/3. Multiplying that by 2 gives us 2/3 for pi1. So, in the long run, roughly 67% of days will be sunny and 33% will be rainy. Now that we have calculated both short-term and long-term probabilities, let us look at a visual representation of our system. This is a state transition diagram. The large circles represent our two states, sunny and rainy. The directed arrows show the exact probabilities of moving between these states from one day to the next. Notice how the arrows leaving the sunny circle, 0.8 and 0.2, add up to exactly 1, perfectly matching the rules of our matrix. We have covered a lot of ground today. Let us review the key takeaways. A transition probability matrix is a mathematical engine that captures the exact chances of a system moving between states. Remember that every row must sum to 1. You can predict multiple steps into the future simply by multiplying the matrix by itself. Eventually, systems settle into a stable equilibrium distribution. Mastering this unlocks the ability to analyze random processes in search engines, genetics, and queuing theory. Great job today.